In this video, we're going to see how we can use derivatives to find the local maxima and local minima of functions. So let's get started. The first derivative test tells me that if c is a critical point, and a critical point is just a point where we know that the derivative is equal to 0 or the derivative doesn't exist, and I know that f is continuous at c. If there is a positive number delta such that we have this, that f prime of x is positive for all points x between c minus delta and c, and that f prime of x is negative for all x in c plus delta, then f has a local maximum. What this is telling me is that if the derivative is positive to the left of c and negative to the right of c, then the function has a local maximum at c. The same thing if I know that my function f has negative derivative to the left of c and positive derivative to the right of c, then my function has a local minimum at c. And now if the derivative doesn't change sign to the left and to the right of c, then it doesn't have neither local maximum nor a local minimum. So I'm not going to write down the proof. The proof is actually not very difficult if you write down all the definitions of what each thing means. And well, here we know that in particular, if the derivative is positive, my function is going to be increasing, and then if the derivative is negative, then it's going to be decreasing, and then try to write all those things down. When you combine them, the proof is not too complicated. What I want to do is we're going to take a look at vectors and see what this tells me. You see, if the derivative at c is 0, and then the derivative is positive to the left of c and then negative to the right of c, then we go up and then down. And the same thing when my function is not differentiable at c, we went up and down, we just had a corner there. Again, we have a scenario where we have negative derivative to the left of c and a positive derivative to the right of c. So we went down and then up, so that gives us a local minimum. And here we have again two pictures, one where the derivative is 0 and one where the derivative doesn't exist at c, so we have here a corner. And then we have the scenario where the derivative is always positive in this case, so my function goes up, kind of takes a little bit of a break, and up again. So my function is still always increasing, there is not a local maximum, there is not a local minimum. And again, we have this second picture here, we had a vertical tangent line, so it's not differentiable, but again, like function, it keeps kind of going up, so there is no local maximum or a local minimum. And now in this example, we're going to find the local maximum and local minimum values of this function given by f of x equals x to the 4 over 4 minus x cubed plus x squared plus 1. So the function is a polynomial, therefore is everywhere differentiable, and when we take the derivative, we end up with just we end up with x cubed minus 3x squared plus 2x, and we can just factor this as x times x minus 1 times x minus 2. And we want to know when this derivative is positive and when the derivative is negative. I created here a table to note the signs of each one of these three linear polynomials in those intervals. So I took the points where the derivative is 0, which happens at 0, 1, and 2, and I split the real line into the intervals negative infinity to 0, 0 to 1, 1 to 2, and 2 to infinity. Then now x is going to be negative anywhere that is less than 0. X minus 1 is negative for any points that are less than 1. And x minus 2 is negative for any points less than 2, and it's positive everywhere else. And now we just need to study the product of these three things. So you see, if x is less than 0, then we have a negative. All the three terms are negative, so the product is going to be negative. But between 0 and 1, have that x is positive, x minus 1 is negative, x minus 2 is negative. So we end up with negative. So it's minus, plus times minus times minus, it gives you a plus. So here we have this table that summarizes everything. So the derivative is negative, the interval minus infinity 0, and the interval 1 to 2, and is positive in the interval 0 to 1 and 2 to infinity. So this gives us an idea of where the function is decreasing and increasing. So it goes down, then up, then down, then up. So using the facts that all the theorems that we've seen before, we know that my function decreases on the interval negative infinity to 0 and 1 to 2, increases on the interval 0 to 1 and the interval 2 to infinity, and we can then see that the derivative changes from negative to positive at 0. So there we have a local minimum. We have another local minimum at 2, because again we go from negative to positive, and then we have a local maximum at 1, because the derivative goes positive, then negative, so we go up and then down. And just to summarize, here is the graph of my function. So as you see, exactly at 0 we have something that looks, like a local minimum. At 1 we have this bump, local maximum, and then again a local minimum at